The World Health Organization estimates that 13% of the global population suffers from a mental health disorder. Identifying who needs help before a crisis occurs requires analyzing a massive web of human variables. Researchers analyzed a publicly available dataset containing survey responses from tens of thousands of individuals across the United States, Canada, and the United Kingdom. This data includes 3 distinct layers of information. The first is immutable demographic profiles, such as a patient's age, gender, and geographic location. The second layer tracks self-reported behaviors. This includes lifestyle metrics like whether someone is self-employed and exactly how many days they spend indoors. The third layer introduces linguistic sentiment. Researchers ran natural language processing on the respondents' text answers to generate mathematical scores for readability and emotional tone. The core objective is to synthesize these 3 disjointed data streams, who you are, what you do, and how you speak, to predict whether a person will seek professional mental health treatment. The primary obstacle is that behavioral tracking and linguistic sentiment are inherently noisy and highly subjective. Traditional statistical models struggle to process this level of noise. When applied to highly irregular human behavior, strict linear equations often fail to map the true risk. Accurate risk prediction requires nonlinear ensemble algorithms. These machine learning models are designed to map the complex, overlapping dependencies that define our psychosocial lives. Developing a methodology that can synthesize these disjointed inputs is a necessary step towards shifting psychiatric care from reactive treatment to proactive digital triage. This distribution chart shows reported stress levels across all dataset respondents. The right-skewed data means the vast majority report mild to moderate stress, while only a small minority register severe stress. This suggests severe mental strain is a concentrated outlier. This bar graph tracks the proportion of individuals who sought mental health treatment, segmented by gender. The distinct height difference between the columns illustrates a clear behavioral gap, aligning with literature showing females pursue professional help at higher rates than males. Because human behavioral traits are skewed and heterogeneous, the mathematical models analyzing them must be flexible enough to accommodate data that does not fall into symmetrical curves. To establish a baseline, the researchers first tested logistic regression, a standard interpretable statistical model used widely in clinical literature. The logistic regression model capped out at an overall accuracy rate of 70.3%. The limitation stems from the model's mechanical assumption. Logistic regression attempts to draw a straight, rigid boundary between individuals who are at risk and those who are not. Classification errors occur where complex patient profiles cross over this flat linear boundary. Human behavior does not operate in isolated, independent silos. Every action and environmental pressure interacts with the others. A nonlinear interaction occurs when 2 variables multiply each other's effects, depending on the specific context. Take a patient experiencing high economic stress while simultaneously enduring prolonged indoor confinement. These 2 variables compound each other. The isolation removes the coping mechanisms needed to deal with the financial strain, creating a risk profile greater than the sum of its individual parts. Linear coefficients cannot calculate this compounding effect. They evaluate economic stress and isolation entirely separately. Applying rigid linear rules to human psychology artificially suppresses a model's predictive capability. To solve this, the researchers deployed a random forest algorithm. By utilizing an ensemble approach to capture nonlinear dependencies, this model achieved 73% accuracy. Instead of relying on one rigid boundary, a random forest generates multiple branching decision trees. It divides the data over and over, isolating interacting variables into precise, multidimensional pockets. By combining the predictions of all these individual trees, the ensemble architecture averages out the noise inherent in self-reported survey data, protecting the final prediction from overfitting. This is a receiver operating characteristic curve, measuring the model's discriminative capacity. The blue line's trajectory toward the upper left quadrant results in an area under the curve value of nearly 0.80, validating the model's ability to differentiate between the 2 outcome classes. The mathematical structure of the random forest effectively mirrors the compounding complexity of human psychology, making it a suited tool for psychiatric data. This confusion matrix displays how the random forest distributed its errors, specifically the false negatives in the bottom left quadrant. In public health, this represents an at-risk individual failing to trigger an intervention. The random forest achieved its superior scores by minimizing these false negatives. In medical predictive modeling, raw accuracy is secondary to a model's utility in identifying vulnerable populations. Beneath the math, which exact human variables was the algorithm prioritizing to make its predictions? This chart ranks the top 10 feature importances from the model. The highest-ranking predictors are dynamic psychosocial behaviors, specifically growing stress and economic strain. Directly below sits environmental isolation, represented by days indoors. These lived experiences heavily outrank immutable demographic traits like gender. The model also extracted predictive value from subtle linguistic sentiment scores. Minute fluctuations in text tone proved to be reliable indicators of emotional distress. These computational findings directly validate sociological theories that link chronic environmental stress and socioeconomic instability to psychological decline. The algorithm empirically proves that a patient's dynamic lived experience is a more accurate predictor of a mental health crisis than their static demographic identity. Applying these findings to a clinical setting alters the traditional intake process. Static demographic checklists can be supplemented by systems capable of ingesting diverse, continuous data. By synthesizing multimodal data, from text sentiment to daily habits, clinicians can build a continuous diagnostic heuristic that updates a patient's risk profile. These machine learning models are not designed to replace diagnostic psychiatrists. Their actual function is to operate as a digital triage tool. The algorithms flag behavioral shifts in the background, triggering early human intervention. However, this specific study is bound by a primary limitation. It relies entirely on cross-sectional survey data, a snapshot of a patient at a single moment in time. Self-reported cross-sectional data carries inherent flaws, such as recall bias and social desirability, where patients may underreport their actual distress. While cross-sectional data proves the concept, static snapshot cannot fully capture the evolving temporal dynamics of a patient's psychological journey. The next generation of predictive models requires a transition from static surveys to continuous longitudinal time series data tracking. As the technology matures, subjective survey responses will eventually be replaced by objective biometrics and continuous behavioral tracking. Deploying these advanced models requires mandatory ethical frameworks to ensure rigorous data privacy and to actively prevent algorithmic bias. The potential of computational psychiatry lies in combining the capabilities of Ensemble machine learning with ethical standards to deliver proactive public health interventions.